Swayam Prabha. Digital India. Educated India.
Good afternoon. So, in this lecture, I'll be talking about polyhydroxyalkaonates. It's a type of a polyester that is made completely from biological origins. Both the substrates as well as the synthesis, all from bio. So, this PHA kind of has a huge potential in synthesizing bio-based material, renewable polymers. So I'll talk about today about its characteristics, how it is synthesized, and what are the blends, which are the companies that they are making them. So next to PLA, PHA is gaining a lot of traction in various fields, especially in biomedical applications. Okay, some introductory remark. So polyhydroxyalkaonates, this is a family of biopolymers, and this is synthesized by several kinds of bacteria. Okay, and these bacteria they make these polyesters or polyhydroxyalkaonates to kind of store as a intracellular carbon and for energy storage as granules. And these bacteria basically uses some sugar or biomaterial, substrates, and then they ferment it to make into this polyhydroxyalkaonates. So PHAs are eco-friendly material because it is based on biorenewable materials, and they are also biodegradable both in soil, marine conditions as well. It has an excellent biocompatibility. That means when this polymer is in contact with live tissues, so tissues do not feel any toxicity. So it's very good for biomedical applications such as tissue engineering and scaffolding. In the past, we have looked at other polymers, biopolymers like chitin, chitosan, pectin, as used as a biomedical hyaluronic acid and so on. So in that light, PHA is also very useful in biomedical applications. So this polyhydroxyalkanate is a family name. Okay, we'll come to the chemistry later. So in terms of classification, we call something called short chain length PHA and medium chain length PHA. It depends on how many carbons are there in the repeating units. Okay, this doesn't mean the total polymer length. It just means in the monomeric unit, how many carbons are there. If the number of carbons are 4 or 5, we call them as a short chain PHA. And if the number of carbons in the repeating units are more than 6, we call them as a medium chain length PHA. Okay. So now, if you look at the chemistry or the chemical aspects, so this is a formula. The repeating units is shown here within this bracket. Okay, so there is a CO bond, carbonyl bond, and there is a CH2. This X is a variable. X can take different values, and then you have this RCHO and this repeating units. So here there is I think about 150 different kinds of PHA molecules are available, depending upon what is the value of X and what is this R here is. Okay, so the most simplest thing would be X value of 1 and R is having hydrogen. That means you have HO, CO, CH2, CH, and this is H. So this is called poly-3-hydroxypropionate, or in short we write P3HP. Okay, so this this is the most simplest PHA you can think of. Next is, instead of this hydrogen here, you can have methyl group or CH3 group. Then we have something called P3HB. Okay, so that would be written as HO. X is 1 here. So here you have CH3 group. So this is called the poly-3-hydroxybutyrate, or in short P3HB or just PHB. Then suppose if you make this length larger from methyl to ethyl, if you go, then you have polyhydroxyvalerate, which has a structure of COO, CH2, CH. Here you have CH2, CH3. So this is the ethyl group. So depending upon whether you have hydrogen or methyl group or ethyl group, you have different polymer. So the moment you change one side chain group, then the property also is going to change. Okay, so and then there are also other things. For example, if you consider the P4HB, so here X is equal to 2. That means this will have a CH2 CH2 group. So let me write this here. O. So here you have 2 repeating units of CH2 CH2. So this is called P4HB or simply PHB. P4HB. Okay, so the difference between P3HB and P4HB is that whether you have single methyl group or you have a 2 methyl group. Depending upon that, you have, and then you can see that you can have the side groups going all the way up to nano, octyl, and nonyl, and pentadecyl. So you can really grow this chain very long. Okay, and based on that, you can have different kinds of polymers. So this is PHA chemistry. It has a particular function, particular structure. Only the side group chain length can be increased, and also the CH2 group can also be increased. Okay. So of all these, the common polymers, when we say PHB or PHA, the common polymers are PHBs, PHB, PHBV, and so on. And also, they are not really homopolymer. They can also form a copolymer. For example, here you can see it is a copolymer of P3HB. This co means copolymer with P3HV. Okay, so P3HB and HV are these two. So basically, if you have these two groups together, then you have what is called the PHBV. Okay, it's basically a copolymer, and you can see many other combinations. You take any two of those PHA, and if you can copolymerize, then you have this. Actually, you don't copolymerize. The bacteria, when they synthesize, they mix match different kinds of monomers, and then you get different chemistry. For example, here I already showed you this. So P3HB is this, and then the PHBV, you can see that there is one group here which is PHB, and this is PBV, right? So you can see that two are actually combined together as a copolymer. And there are many other combinations you can think of, but these are the top 5-6 polymers that you often see in the market which are sold. Okay, so these are homopolymers, and these are all copolymers. Okay, based on different chemistry. So in terms of synthesis, this TM diagram shows that this is the entire cell, and then you see this white color granules. Those are basically PHB. Okay, so you can see that each cell has one or many kinds of PHA granules. So PH is synthesized through bacteria, and typically when you treat this bacteria under some deficient conditions, like for example when you make phosphate, nitrogen and oxygen deficient, then the cells try to actually produce this under stressed conditions. In a normal condition they don't produce this, okay, but when you stress this bacteria, then you have production of PHA in those bacteria. Now in terms of the mechanism how they form, it is found that there are about 3 enzymes that are relevant. So there is something called PHA synthase, in short it's written as PHAC, and there is something called 3-hydroxybutyryl coenzyme A, and then phasin. So these are the 3 enzymes that are known. So if you look at the mechanism, they say that you got this bacterial lipid membrane, and in that you have this PHA synthase enzyme attaching to the head groups, and then the other enzyme, hydroxybutyryl coenzyme, as well as phase enzyme, they together synthesize this polymer in the inner hydrophobic regions of the lipid. Okay. So as you grow, as this polymer gets longer and longer, they basically form a small granule, and this granule is what you see inside the cell. Okay. So these are the three important enzymes that that have been identified as a key enzymes for this. So if you look at biochemical pathway, basically what happens is, first you have some substrate fed to the bacterium, right? And so what first step is, there's a substrate is now converted into an acetate. Okay. Then this acetate is actually attacked by an enzyme cofactor CoA via a thioester bond. So this is the thioester bond. Okay, this CoA is the enzyme that basically forms with the acetate and form this acetyl CoA complex. Okay, this is another acetyl CoA complex. So prior to this, there should be a fermentation process where the substrate is converted into acetate. Your sugar substrate is actually glucose or fructose, all that starch, all those substrate is converted into acetate. Then this acetate is attacked by this CoA enzyme to form a thioacetate bond. Then two of these form together to form a acetoacetyl dimer. Okay, so you can see that two such acetyl CoA combine together to form a dimer called acetoacetyl CoA. Then this is actually reduced by this nicotinamide adenine dinucleotide phosphate, in short NADPH. So NADPH will actually reduce this dimer to form 3-hydroxybutyryl coenzyme. So this is your monomer. Once you have this monomer, then this can be polymerized by removal of this enzyme, and you can see that from here to here we have basically a polymerization of the monomer. So that's the kind of proposed mechanism for how bacteria converts the substrate into a PHA molecules. So here is a list of bacteria that has been reported. Some of them are wild, some of them are actually recombinant, engineered so that they can actually produce these polymers. So I think among them, this Cupriavidus nectator is the most commonly used, most widely studied bacterium. So you can see that it produces PHB, PHBV copolymer, and also various other copolymers. And there are a few other enzymes, and then there is a corresponding list of copolymer that is generated. So they also have said something about, for each of these bacterium, what's the specific substrate should be provided so that they can produce this particular enzymes. So you can see most of them are actually copolymers, depending upon the different types of bacteria. Does anyone work with this kind of bacteria before? Okay, fine. Okay. Now, if you come to the property of PHA and what it can replace in terms of the conventional plastics, so it finds applications in making bottles, bags, containers, as well as consumer applications, and then also you can add along with this a lot of biomedical applications also. Sure, tissue scaffold. Etc. And so in terms of the its property, PHA is actually opaque, it does not form a clear film, So that is because it actually forms it's basically forms a semi-crystalline polymer, but the crystal sizes are so big, and that makes them opaque. And as I said, PHA is biodegradable both in soil and marine. It has a thermoplastic nature in the sense that it has a melting temperature anywhere between 40 to 180, because the range is so wide, because the polymers can have different copolymers, so it's very broad. And there are studies which says that it forms nice crystals, and the lamellar thickness can be anywhere between 4 to 7 nanometers. So this mineral PHA is a commercially available PHA in the market, and so here its property is compared with other commodity plastics like polypropylene and HDPE. So if you see, the specific gravity or the density is quite high compared to your polypropylene or HDPE. And in terms of yield strength, they are quite comparable. You can see it's about 24 megapascal versus 33 for polypropylene and 21 to 35. So it's kind of nicely overlaps with the yield strength of polypropylene and HDPE. But when it comes to elongation at break, this is only 7%, whereas HDPE can go all the way up to 1000 to 2000. So in elongation at break, it has kind of very brittle feature, whereas PP and HDPE has higher elongation at break. In terms of flexural modulus, pH has as good as PP, as well as HDPE. Heat distortion temperature is about 123, which is higher than polypropylene and HDPE. Okay, so heat distortion temperature is basically the temperature at which the material will actually deform under certain applied load. Okay, so it can actually withstand very high temperature. Okay, so these are some of the properties. I mean, I'm not giving details of all this, how it is obtained, but this is a kind of a range of material properties one can expect. So except the elongation at break, pretty much all the other properties are very similar to polypropylene and HDPE. So that means if you want to replace HDPE or polypropylene, and PHA probably is the way to go, unless you want to have a very long film with a high elongation at break. Apart from this, there is also very well known limitations of most of the PHA. As I said before, PHA forms a crystalline polymer, but it forms a very large crystal that makes them opaque. If the crystal size is more than the wavelength of light, you will see that this light will get scattered, so you will see a very opaque film. So there's a lot of research opportunity to control the crystal growth by adding something like, you can add a nucleating agent, create more number of nuclei but smaller in size, so that you can form a transparent film and transparent materials. And the melting temperature of PHP in most of them is very close to the thermal decomposition temperature. That means when you try to inject mold, or when you try to thermally process, if you don't control the temperature, you may actually degrade the material. So it's very important to keep the temperature tightly focused. And it also undergoes thermal degradation in the conventional thermoplastic processing techniques. So we have to keep a proper check on this thermal degradation. So these are some of the very well known limitations, not only for PHA, for any other material like chitosan, pectin, starch. Most of these biopolymers also have a similar kind of limitations. So what do we do? So what do we do in this case? How do we improve their properties? Composites, fillers, additives, plasticizers, right? So PHA also has been very widely studied in terms of adding fillers or blending or adding plasticizers. So here I have given some some sort of keywords, but each one of them you'll see tens of hundreds of papers in each case. Okay, for example, to improve the mechanical property, so there are studies where the layered double hydroxide clay have been added to PHA matrix, or cellulose whiskers, or hydroxy apatite nanoparticles. Okay, so these are added to the PHA polymer to actually improve their mechanical properties. In terms of processability, plasticizers are added. Examples are dioctyl phthalate, dioctyl sibacate, and acetyl tributyl citrate. These are commonly used plasticizer for this particular polymer. Okay, we have seen other plasticizers like sorbitol, ethylene glycols also. And then apart from that, PHA has been also used along with the natural fibers like kenna fibers, cellulose fibers like rice straw and wheat straw, all those things. Apart from this, additives, they are also blending. So PHA blended with starch, blended with ethyl cellulose, cellulose propionate, cellulose acetate butyrate are also common. Recently, PHA has been blended with the lignin also. PVA, polysaccharides, caprolactam, polyvinyl phenyl, polyvinyl acetate, even PLA, and then xylogen. Okay, it's been blended with many of these in order to kind of improve the thermal property, mechanical property of desired applications. Recently, there are a lot of development happening in grafting. That means you take your PHA and then chemically link another polymers or functional groups. For example, there's one study in which PHA and chitosan are actually grafted. Chitosan has, what are the functional groups of chitosan? What are the functional groups available in chitosan? You wrote exam. So it has an amine group, right? Amine. So this amine group can be actually functional, can be activated to actually bond with PHA molecules. Okay. Similarly, PG is polyethylene glycol, and PMMA, even PLA, PCl. So you have a lot of chemical option to directly graft many of the polymers with PHA. Okay. So the PHA, for its biocompatibility and biodegradability, along with other polymer that can give more strength, more thermal features, this particular area is kind of open for so many innovations here in terms of what you can graft with. So here is a list of companies that they are producing. So there's one company called Danimer Scientific, US based, and they produce PHA in the product code of Nodax. Its MCL means medium chain length PHA, and they use this for various applications like coatings, extrusions, and films. And this Kaneka Corporation at Japan is producing this PHBH. It's basically a copolymer of P3HB and 3PHXX, and it has been producing some tens of thousands of tons capacity. So RWDC is from Singapore, also has from USA. So they produce a resin called Solone, which is a PHA produced from waste cooking oil as a source, and they've been using for films and packaging. And there are companies from South Korea and China, and you can see that there are production of various kinds of PHA in these things. So in terms of distribution, so the company distribution, you can see there is quite a lot of the previous table showed only few of them, but then this is more exhaustive current as of 2025. These are the companies and the corresponding countries in which they are produced. So you can see a large number of companies in China is producing, and also quite a bit in US also, indicating that, and also quite a bit in Europe, indicating that PHA has a huge potential for medical application with regard to its biocompatibility and functional aspects. But there is no company in India producing PHA as of now. So okay. So with that, if you look at the application, as I said, packaging is promising, but given the cost of PHA is not penetrated yet, but high cost is tolerated in biomedical applications. So that's why you see a lot of biomedical applications like sutures, tissue culture implants, surgical implants, wound dressings, having part of the bones, replanted veins, engineered heart valves and pins. So very many implantable devices are actually made with PHA. In the pharmacological field, encapsulation of medicine for controlled release for drug delivery. In veterinary also, similarly the capsule that are formed through PHA. Agriculture, industrial is also coming up. In terms of our plastic use, bags, bottles, disposable containers, personal hygienes, degradable diapers, and etc. And even for oils will come, applications. So PHA is having a lot of scope. In terms of end of life, you can also kind of repolymerize and then reuse if you like. So it has a huge potential in terms of what we can do with the PHA. So that's all for today. So